Welcome, and thank you for joining us for today's webcast, Method to Reduce Stabilization Time for Shape Memory Alloys, sponsored by NASA's Glenn Research Center and TechBriefs Media Group. I'm Beth Sisk, an editor at TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 60 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the webcast by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered after the webcast, and slides from this presentation will be available under the Event Resources tab. Now, in order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speakers. Dr. Santo Padula II is a materials research engineer at NASA Glenn Research Center. He has worked full-time at the NASA Glenn Research Center for 15 years, focusing his career on developing test techniques to support advanced material development. His research has helped lead to the development of one-of-a-kind models for new materials with unusual behaviors. Santo received his PhD in Materials Science and Engineering from Michigan Technological University. Also on the line with us today is Karen Bartos, the NASA Glenn Intellectual Property Portfolio Manager for the Glenn Technology Transfer Office. In her role, Karen oversees strategic review and processing of technologies from invention disclosure through to commercialization. In addition, she is the technology manager for the aeronautics, mechanical and fluid systems, and propulsion categories of technologies. Karen spent 25 years in Glenn's engineering directorate before joining the Technology Transfer Office. She holds both a BS and an MS degree in mechanical engineering from Cleveland State University. So now I'd like to hand the webcast over to our first speaker, Karen Bartos.
Thank you. Hi, I'm Karen Bartos, a technology manager in NASA Glenn Research Center's Technology Transfer Office. I'm happy to be able to share a bit of information about our technology transfer program at Glenn. NASA's vision is to reach for new heights and reveal the unknown so that what we do and learn will benefit all humankind. In our work supporting NASA missions, we generate intellectual property that has applications outside of the space and aeronautics programs. In other words, we develop technologies and software to solve our NASA mission challenges. These technologies may also be used to help solve problems in a variety of industries. We have been working hard to make our technologies that are available for licensing easy to find. And we have better aligned our intellectual property portfolio to industry needs. Our entire portfolio can be found on our website and can be searched using keywords, patent numbers, or browsed by category. Each patented and patent-pending technology will have a technology solution sheet describing the technology, its uses and benefits, and licensing information. And if you have any questions or need assistance, a technology manager is there for you. The primary goal of the Technology Transfer Office is to make sure that Glenn's technologies are available to industry for commercialization. To this end, all of Glenn's intellectual property is categorized and assigned a technology manager. Our hope is to make the transfer of our technology easy. Although licensing Glenn's technologies is our primary focus, we also welcome collaborative partnerships with other government agencies and companies, big and small, to move our cutting-edge technologies into the marketplace. We can collaborate through reimbursable Space Act agreements, and we provide access to our software through software usage agreements. All of these are handled through the Technology Transfer Office. We are the entry point or conduit through which you can work with NASA Glenn. We've been working hard to streamline the partnership and commercialization process. And as a result, NASA Glenn offers 3 types of licenses to better meet industry's needs. An evaluation license allows you to try on a technology. Its low fee and one-year term are particularly well suited to nascent technologies and attractive to small and growing businesses. Our goal is to help minimize risk while enabling a licensee to fully evaluate a technology and its potential market uses before committing to a commercial license. A commercial license allows a licensee to make and sell products. These licenses are individually negotiated and can be structured in any number of ways. Quick launch licenses are just that, quick. NASA is pleased to offer a specially selected portfolio of technologies available for commercial, non-exclusive licensing. These quick launch licenses have a set initial fee, annual royalty, and standard terms. With quick launch licensing, NASA can quickly turn your license application into a license agreement and transfer our technologies to you. Reimbursable Space Act agreements are unique to NASA and are used for collaborative research and development. Space Act agreements define the project scope, intellectual property and data rights, and the schedule for the project. Software usage agreements allow U.S. citizens and entities access to NASA-developed software. All of the agency's software is listed in the software catalog, and the request process is entirely electronic. I hope that you will look to NASA Glenn as a potential source of technologies and expertise. Here you can see the website addresses for the agency's intellectual property portfolio and the agency's software catalog. These slides will be made available to you after the webinar, and you can always contact me for more information. Thank you for the opportunity to talk about Glenn's Technology Transfer Program. This concludes my portion of the presentation, and now let me introduce you to Dr. Santo Padula.
Hello, everybody. My name is Dr. Santo Padula, and today I'm going to be talking to you about a methodology that we've developed to enhance the stabilization of shape memory alloys for use in actuator technologies. As part of this presentation, because we don't know what the breadth of the audience is going to look like, we're going to go through a little bit of background on shape memory alloys, why the effect happens, and we're going to move into various characteristics that are required to utilize these new class of materials in applications that rival hydraulic and conventional actuation systems. And then we're going to move up forward into a methodology that's been developed here at Glenn that significantly reduces the time to stabilize these materials for their intended service function and is going to allow them to better be incorporated into commercial products. So with that, we'll begin by saying what a shape memory alloy is. And as the name implies, these are new classes of metal systems, predominantly based in nickel and titanium, that have an intended memory, so to speak. What that means is that they can be deformed and returned to their original shape through the application of a solid-state phase transformation that goes on inside of the material as we heat it and cool it. We can look at this effect as in a simple way through the diagram on the lower left, where we take a self-accommodated low-temperature martensite phase that exists in the material, and then through the application of an applied external force on a particular component made of this material, we would generate some level of deformation, as indicated by state 2 there in the lower left, where we've reoriented part of that martensitic structure to accommodate the deformation field that the material would go through the application of load. When we then unload that component, you see that there is some residual deformation present on the part, and that residual deformation, which normally would be looked at as plastic and irreversible, in this case can actually be reversed by heating the component through the solid-state phase transformation to revert it from that reoriented martensitic structure to the parent austenitic structure, which you see over there in red. wherein through the application of that transformation, we recover all of that deformation. Subsequently, upon cooling, we return back to the original martensitic state, where in a macro sense, we have no change in the recovered deformation characteristic, but we've actually reset and are ready for another deformation event. So we can use this cyclically in order to do large deformation fields where we can recover those deformations, in this case through strains, inside the material that significantly exceed any kinds of strains we could put into a component elastically. Conversely, on the lower right, we see the more typical actuator response, wherein instead of having to do the recovery under zero load, we can actually remain in a state where the component is loaded. And now through the thermal transformation, heating and cooling, we can go back and forth between two different states, one martensitic and one austenitic, where we have deformation induced into the component during cooling that is then recoverable through heating. And that gives us the ability to do actuation stroke under load, which then allows us to perform work. So we can do things just like we would do with a conventional actuation system, where we're producing work output on a device. This happens at the atomic level because of the fact that between these two phases that occur in the solid state, the austenite being the high temperature phase, or so-called high temperature, it doesn't have to be actually high temperature, just high relative to its daughter martensite state. We have this small lattice invariant shear that happens between those two phases that, when coupled together across the grain aggregate within the material, can produce large macroscopic deformation fields through the twinning process that happens in the martensite. In essence, what we have is we have 192 single variants of that twin within the martensite that all correspond to a single correspondence variant of the parent phase. And so any deformation fields up to about 4 to 6% macroscopic strain in the martensite can be recovered when we heat to the austenitic phase. So what we're going to do now is we're going to watch a little video. And in this video, what you're going to see is we've got two different structures that were in that original martensitic condition. We've put a large amount of deformation into each of those structures. And then what we're going to do now is we're going to heat both of those structures up across the solid state phase transformation boundary through the application of hot water that we're going to supply to this petri dish when the video runs. And then what's going to happen is as those components are heated through the transformation, they're going to revert to their original structures. So let's go ahead and play the video. And so as you saw in the video, the large deformations that were induced mechanically into those components were fully recovered once the system was heated through the phase transformation. And if this were an actuation system, rather than it being in a free state like this, we would have some sort of biasing mechanism that would then redeform the part in order to have it ready for another actuation cycle. So this is the way that the shape memory effect works in a real component. And so this shape memory effect can be used to allow components to deform in very complex three-dimensional ways, as well as, as in one-dimensional and two-dimensional forms like wires and or bin bar elements. but we can do pretty much any type of deformation condition that you would want to be able to do with a conventional actuation system, now with a very compact and efficient material form. So as we mentioned, if you look on the lower right, concept of that doing actuation as opposed to a free recovery would be we take a mass and apply it to the end of a wire. And that mass would then reorient the martensitic structure and extend the wire. And then upon heating of the wire, the wire would contract to its original length, thereby moving the mass over a distance and creating work output. Then when we cool the system back down, the mass is heavy enough to re-extend the wire, and we would then be ready for cyclic actuation events, as a simple concept of actuation with SMA. Why is that useful to us? It's useful to us because the energy density that are in these materials are so large that they rival conventional hydraulic and pneumatic actuators, but they give us a package that we can do it in a much more efficient, lightweight type of system, compact type of system. In these systems for actuation, we're interested in a number of characteristics within the alloy itself. For actuation, typically we're interested in high transformation temperatures, although there are a lot of applications that we are doing here at NASA Glenn for space where we're interested in cryo application as well. But terrestrially speaking, we're interested in improving the transformation temperatures so that we have more margin and control over when the actuation event is going to happen. Of course, we're always interested in narrow hysteresis within these systems because that improves not only bandwidth or speed of actuation, but it also improves the energy efficiency because we require less thermal input in order to make the actuation systems happen. Large transformation strain and or stroke under large externally applied forces is obviously desirable because we'd like to be able to do as much work as possible and as an efficient a package as we can get. But clearly the most sought after characteristic that's kind of eluded the industry for quite a while is good dimensional stability. Without good dimensional stability, we don't have tight tolerancing on our parts characteristics in terms of its deformation event, and therefore they become less useful or less easily applicable to real commercial applications. So there's a large focus on trying to create alloys that not only have these other characteristics, but have good enough dimensional stability that we can reproduce the actuation event within tight tolerance from cycle to cycle to cycle. What is dimensional stability or instability in these systems? It's the degree of evolution or change in part geometry or tolerancing that happens as we thermally cycle the system under load. So here's here's a typical evolutionary set of curves for a part component that would be like a simple tensile dog bone specimen, where we've loaded it to varying degrees of applied external stress and then thermally cycled it through the transformation. And as you can see, the actuation characteristic that we talked about before is slowly evolving in the deformation field. So we're going from some level of strain around 4% or slightly above it, and then it's eventually evolving with time and reaching a saturated state somewhere on the order of 8 to 12 to 14 to 18%, depending on the external stress that was applied to the system in this particular case. And of course, until that level of walking from cycle to cycle, or level of open loop strain as we call it in the community, until that reduces to a certain level, the reproducibility of the actuation stroke is not good enough to use in an intended application. So how do we determine when it is good enough in terms of dimensional instability? And the way that we do that is we can look at any given temperature during that actuation stroke. We can monitor the evolution of that particular point in the temperature space, we can monitor the amount of strain evolution that's occurring as we cycle the system. And so in the lower left-hand corner, what you'll see is the absolute magnitude of strain that's occurring both at the low temperature side of the actuation as well as the high temperature side. And then we can also monitor the cycle-to-cycle difference of any of those components as a function of the cycle number or time, and watch the exponential decay that occurs in that what we call open loop strain, the epsilon OLS. And so that's an indicator of our stability, because when that open loop strain approaches zero, then we know that from cycle to cycle to cycle, we're not getting any changes in the dimensionality of the component that we're using. And so that's what we're looking for, is to bring that component to a level that when cycled under a fixed stress thermally, we see no dimensional changes other than the one we want, the one between the low temperature state and the high temperature state, and no additional evolution with time. What we've noticed in a lot of the work that we've done using neutron diffraction to study the underlying atomistic structures of these materials through thermomechanical deformation events is that we can see that the deformation state seems to be the key in what's dictating the underlying microstructures and or the stability of these systems. As you can see in the graph here, we're looking at some inverse pole figures which tell us something about the texture of the material, the underlying microstructure that's present at a given state of deformation and or stress. And what you'll see by the vertical lines that we've superimposed on this chart is that the texture is more related to the deformation or the amount of strain that's been generated versus the amount of stress. In fact, if you look at the vertical line that's sitting at 0% strain, what you'll notice is that not only is there a difference in the mode at the 2 points above and below the initial onset point, but there's an almost 800 MPa difference in the level of stress. Yet when it reaches that level of strain, we see the same underlying microstructure. And that, generally speaking, tends to key us that it's the accommodation or the compatibility in this system that is driving things more than it is the internal stress or the underlying stresses that are driving things. So not that both aren't important, both are obviously important, which is why evolution happens, because we are evolving in order to reach an equilibrium point, which is related to the stress fields. But satisfying the compatibility seems to be a big driver in these systems. And so it's this argument that we use to try to move forward in saying, how can we then process differently in order to improve the speed at which we process and get to an underlying microstructure that is equally stabilizing for the component. And so first thing we need to do is we need to look at what's the difference between isothermal stabilization and a conventional training, so to speak, that we would do in the field. And conventional training is really nothing more than what we call an isobaric condition, where we've basically done exactly what we do to use the material as an actuator. We load it with an external stress, and we thermally cycle it, and we wait for that evolution to occur and for saturation to happen. Now the problem with that is that although it will saturate the component deformations quite well, and it will make it useful as an actuator, the issue is that in real applications with large-scale structures, this can take on the order of weeks or more to accomplish, depending on the thermal mass that's in the component, the size of the component, and the stress level that's desired for the actuation element. And so this is prohibitive to us in the sense that taking 2 to 3 weeks to stabilize each component that you're going to use in service in a commercial product is not very desirable. So it'd be nice to be able to develop a system or another thermomechanical methodology that allows us to stabilize the material for this same type of condition, but in a different way that allows us to do it much faster. And so the concept that's been developed here is an isothermal training where we're using mechanical cycling at a fixed temperature to achieve the stabilization process. And in the limit of this, we can accomplish the same thing we would do with a conventional training with a single mechanical loading and unloading of the component. This then allows us to reduce the stabilization times from the order of weeks down to the order of minutes or even seconds if you have the right apparatus. And so we're going to look more closely now at the methodology that's used to do that, or one of the methodologies that's used to do that. So how is the isothermal stabilization condition determined? Well, unfortunately, as of right now, we still have to run a single isobaric condition on the component. So in other words, put the component into the normal use conditions that it would see as an actuator and let it evolve up to a point where it does stabilize. What that allows us to do is, as we watch for our desired level of dimensional stability, as you see over in the lower right, once we cross the point where we're satisfied that from cycle to cycle we're getting the repeatable performance that we want, we then look at the deformation state that corresponds to that level of dimensional stability that we consider good. That deformation state, generally speaking, we look at as the absolute value of the strain that's inside the component. And once we know what that absolute level of strain is, and that can be taken off at any temperature. It could be taken off at the room temperature or the low temperature side. It could be taken off at the high temperature side. It could be taken off anywhere in between. As long as we know where that is, we can use that deformation state to then determine from that deformation state, which we see on the left here that we pick off, we can use that deformation state to then determine how far we need to load at a given temperature in order to achieve that same deformation state. And so once we've achieved that same deformation state, we can then take that component, put it back into the actuation thermal cyclic condition, and it should therefore be stabilized against further dimensional instability changes. And so, as they say, the proof is actually in the pudding. So this is an indication here. We're going to walk through a couple of different examples to show you that that condition actually will equally stabilize the component. So for the most readily used commercially available material for actuation, the high temperature binary 55 nickel titanium alloy, we would see that material as a very highly evolving system. In fact, here at Glenn we call it a type 2 evolver, so it's a high evolver, low transient type system. And so in that case, if we were to run a simple tensile dog bone in a isobaric condition where we've loaded it to 100 MPa and then held that 100 MPa and thermally cycled it back and forth between room temperature and 165 C, we would see that system evolve like you saw in previous curves. That system would evolve to on the order of about 14% strain before it reached a level that we would consider it dimensionally stable. Okay, so if we now take a virgin material, virgin tensile specimen, and we know that the level is 14%, but in this case we're going to do some isothermal deformations on that material that wouldn't reach that level of the deformation state. And in those cases, what we should expect to see is that if we haven't reached that level of deformation state, when we then take it and put it back into the actuation condition thermomechanically, we should see the system continue to try to evolve because it's not stabilized yet. And so what we see here in the upper left-hand corner is that if we do an isothermal deformation at room temperature, but we only reach about 2.5% strain, when we now take that prior deformed material, which has been deformed priorly isothermally, and we flip it back over to the isobaric 100 MPa condition, we see in the chart sitting over on the right-hand side, this is the M270 case, we see that as we start thermally cycling that system under 100 MPa, indeed, there is still open loop strain developing. So we start off at about 0.6. In the second cycle subsequent to the processing, we go to 0.4, and we're continuing to go down on that exponential decay curve, meaning that the system has still not been stabilized. As we start over with a new piece of material, and we go to the next condition, which is the 290 MPa condition, we've now generated on the order of about 4% strain. And when we then take that material and put it back into an actuation condition under 100 MPa load bias, we see that the M290 condition now starts at a lower value, it's the blue dot, starts at about 0.4% open loop strain, and starts its exponential decay down. We can keep doing that, but of course we already know we've put this material into a condition where we've watched where the actual stabilization occurs. It occurs about 14%. So if we run the case now in the lower right-hand corner of those blue curves, isothermal tension curves, we see that we've generated now about between in the table 13.4 in the martensite unloaded condition and 16.23 in the martensitic loaded condition. We've generated that necessary amount of deformation in the field of the material such that when we now take that material back into the actuation condition of 100 MPa load bias, you see the cyan dot there for the M800 is 4 different cycles right on top of each other where the material has been fully stabilized against the isobaric condition using a mechanical isothermal loading and unloading. And in the extreme case of this, we can do that with 1 loading and 1 unloading, and the material is fully stabilized against any thermocyclic deformation at that level of stress. And so this is something that is of great value to the industry. We have intention to push it even further. This has been done predominantly for tensile deformation as of right now, tension and compression, a little bit of torsion as well. But there are a host of other path dependencies that we can utilize in order to multi-axially stabilize this against other modes of loading so that a given component of material can be processed in a way that it could be used for tension, compression, and or shear instead of only one methodology and still have reproducible performance. So with that, we'll summarize and say that dimensional instability is a very common problem that is oftentimes sought after and addressed when dealing with SMA components and technologies. The conventional approaches that we utilize do quite well in allowing us to have repeatable performance under the intended operating stresses. But those conventional processes are extremely time-consuming, and there's a great desire to reduce the amount of time to train conventionally from the order of weeks down to something more manageable like the order of minutes. And so this alternative approach achieves that desired stabilization significantly faster, reducing those times greatly while simultaneously producing equivalent stabilization results. And the only thing that it requires is a priori knowledge of the end material state that we want to stabilize for, given the loading that we're going to put on the intended component for service. And so with that, I think we'll turn it over to the question and answers.
Okay, well, thank you for your very interesting talks. At this time, we're going to begin our Q&A. If you have a question, please submit it by entering it in the box at the bottom of your screen. We're going to start with the questions we've got on hand. We've got quite a few here. First one is this approach related to the Strain Thermal Energy Recovery Program?
What was the question?
Is this approach related to the Strain Thermal Energy Recovery Program? That's what was typed in by one of our listeners.
I'm not sure that I understand what he's asking.
Okay. Then let's go on to the next one. Is this approach limited to room temperature deformation?
No. So on the second one, on this question, so any point, once we know where the system has stabilized in the field, which is, can I go back through the charts to answer these questions? Is that okay for me to cursor back through these slides?
Yep.
Okay, so as you see here on the screen, all of these evolutions that have happened under different levels of stress have achieved a different state at the end. So if you look at that last last part of the conversion curve, where let's say in the lower right-hand corner of the 300 MPa, we're going from 16% at room temperature to about 165, so to about 13% at 165 degrees C. Anywhere along that curve, we could pick off both a temperature and a magnitude. And so if we did the isothermal deformation process at a given temperature, we just need to know what level of deformation we should be at that temperature. And as long as we reach that level at that temperature, we will ride on this final stabilized curve in a subsequent process. So the deformations do not have to be, and in fact in a lot of cases they shouldn't. We used room temperature as an indication that it can be done anywhere in the field, because typically we would rather process at higher temperature. We get less damage accumulation when we do that. But the point is, in this system, because of how far these damage mechanisms are pushed out in terms of the strain field, we can process almost anywhere we want as long as we know what that target end deformation state is. I hope that answers the question.
Okay, the next question is, are you able to condition the total sample or just a local area?
In this case, this is the whole specimen. That was because this was in a homogeneous state of deformation. But that's the point. The point is that it doesn't matter if it's a homogeneous deformation field or a heterogeneous deformation field. As long as we know what that deformation field should look like in the two stabilized conditions that we want to attain, then we can process that component if we have a methodology to do so. We can process that multi-axially and achieve the desired outcome.
Okay. The next question is has the actuator system been researched for flow controls?
We have done a number of applications where we've looked at flow control type devices or valves. The limiting issue with shape memory really comes down to what bandwidth do you need, because the only thing that governs the transformation in these systems is a heat transfer problem, getting the heat in and out of the component. And so if you need a bandwidth that's higher than what you can do in your heat transfer problem, they won't work for your application. But outside of solving the heat transfer problem, being able to get the heat in and out of the component fast enough for your application, these materials have been looked at for all kinds of things, including flow control devices.
Okay, I've got two questions I'm going to ask you together because they're very related. Have you tried any other SMA alloys, and have you tried other SMA compositions with this approach?
With this particular approach, we have not validated this methodology, but we do work heavily here at NASA Glenn with a number of different alloy systems, mainly based on nickel and titanium. But we are doing ternary and quaternary alloying additions, and we have suites of alloys that go everywhere from the cryo regime up to 300 to 400 degrees C. But none of them have actually been tested in this capacity to validate the dimensional stability. But from a fundamental standpoint, this will work on anything.
Okay, the next question is, will 800 MPa damage the material? Will it microcrack?
We have not seen any level of microcracking. In fact, evolutions that we've done on these materials out to an excess of 30% elongation strains under isobaric conditions have shown that the material is actually still homogeneously deforming. And so we're well away from levels of, at least in 55 nitai, we're well away from levels where we're inducing any actual damage to the component. That may not be true for other systems that are heavily precipitated, but that's the key in this methodology is finding a temperature and path dependency that you can use in an isothermal methodology to generate the level of deformation you need in the component to stabilize it. And that's the key really in any system, is making sure that the temperature and the path, stress path that you're using are generating deformation without imposing too much damage for what you're doing. And that's why it's nice that you can use it at any temperature you want through what you would use in an actuation event. You can process at any of those temperatures and it works just fine.
Okay, we've got a lot of questions to try to get through quickly. So has this approach been tested on SMA foils?
Have not done any work on SMA foils. We're at NASA, unfortunately, working a lot more with bulk actuation systems that are large enough to replace conventional hydraulic systems on aircraft and things of that nature. So we don't do a lot of thin film work. So I can't answer that directly.
Okay, this one says, if you have an actuator with a geometry with many strain states on loading, for example, a system of nickel titanium struts where there's a combination of tensile, and bending strains or varying magnitude, will this type of approach work?
And the answer to that is I don't know, to be honest, because that condition is a very complex condition. And in a particular thing, like if somebody's thinking of a metallic foam or a lattice block structure or something of that nature, we find it much harder to assess the actual strain state as opposed to the displacement state or deformation state. And so in those cases, what to target in terms of the level of deformation becomes a lot harder to deal with. But if there was a way to determine the level of strain that was being developed in that component to stabilize it, then if a process could be put together in order to achieve that level of strain inside the individual elements of the struts, then it would equally work.
Okay, are there any dependencies of this technique on the material composition? For instance, percentage of nickel titanium or effect of other material additives to the alloy mix?
So the answer to that is probably yes. In terms of single-phase material like we see with tie-rich systems, This, I believe, will work equally as well, although we have not tested it for other alloy systems. But for the nickel-rich side of the shape memory alloy systems, where we're heavily using aging to heavily precipitate things, there are differences that will happen in terms of reductions in ductility limits that we can use in order to drive these states. And so only from that perspective do I think that there is potentially an issue, in the sense that once we have highly precipitated systems, we change the characteristics of how much deformation we can put in isothermally without creating damage. So we want to obviously avoid damage within the component while processing to try to achieve dimensional stability for the actuator system. So in those regards, yes, there are some differences.
Can you talk some more? Okay. Can you talk some more about the lifespan of nickel titanium after the stabilization?
So in general, if we again stay away from high damage in the material, depending on how heavily the component is loaded, dictates the lifing of the system. This is true in any shape memory alloy. It's the life of the system is dependent on how close to the limit surface of the transformation we're trying to drive the system. So, in other words, if the actuation system can generate 4% strain in a given condition, but we design the component to only have to deliver 2% strain, we can have hundreds of thousands or millions of cycles. And so with this process, that's one of the keys. One of the keys is we've used an isobaric condition to target only the level of deformation we have to put into the component to reach stabilization. So we're only driving the material to a state where we know once we've reached that level of deformation, we can stop. We don't have to put in extra cold work or other things that would normally reduce our lifing potential. We're putting in only the targeted amount of deformation that we need in order to produce stabilization. And so in that sense, we're maximizing our life to as much as possible. But that life will still be dictated by the magnitude of the stress now that we apply to do the actuation event. And so it's a little bit open answer, but the underlying construct of it is we've done the best that we can do by minimizing the amount of deformation we have to put into the component to stabilize it in order to produce the maximum life that we could possibly get, rather than just throwing an arbitrary 30% cold work into the material, which may stabilize the material, but has also produced some damage and other things that is going to reduce our ductility.
Okay, the next question is, have you looked at the amount of two-way shape memory effect that this method of training produces?
We have not studied that, although we know there will be internal stress inside of the material, which will produce two-way, but we have not studied that in great detail for this particular processing methodology at this point.
Okay. The next viewer asks, did you need to control for sample heating during strain cycles? And if so, how? And what were the strain rates tested?
Can you say the question one more time, please?
Sure. Did you need to control for sample heating during strain cycles? If so, how? And what were the strain rates tested?
So I'm assuming that he means in the post-process material when we thermally cycle the system under isobaric conditions. Yeah, we control the thermal cyclic condition to about 30 degrees C per minute. That's the heating and cooling rate. And what was the second part of the question?
What were the strain rates tested?
Strain rate. The strain rates varied anywhere from about 10 to the minus 5 per second to 10 to the minus 3 per second.
Okay. All right. How many number of cycles are needed isothermally to minimize OLS? And how will this approach vary, for example, with springs?
Okay, so that's a very complicated question. So in the first part of that question, like we've mentioned before, the limit on this is a single loading and unloading. Okay, so I know that we showed mechanical cycling there. Mechanical cycling can be used because I can in an isothermal process, I can go to a lower level of stress. Like let's say I have an issue where if I go to too high of level stress, I'm going to create damage. If I do a control mode where I do load control, both loading and unloading, then I will force the conjugate response of evolution and strain or displacement. So I can go to a lower level of stress and I can mechanically cycle hundreds of thousands of times very quickly and have it evolve to that point in deformation space, 14%. Okay, I can do mechanical cycling faster than I can ever do thermal cycling. So if I have to reduce my levels of stress, I can drive the evolution mechanically to get to the desired state. Now, in any given case, what I'd really rather do is pick a temperature and isothermal stress path that allows me to do it with a single loading and unloading. But sometimes I can't get there depending on these material issues. So I use this construct both cyclically or in the limit, a single loading and unloading to achieve that desired state. Now, with a spring, the issue comes in that I'm no longer a homogeneous field of stress or strain. And so in that case, I have a much harder time determining what is the level of strain in my component that I need to reach in order to get to stabilization. And again, we come back to that process where we say, if there's a way to link that stabilization strain that's happening in my component to that, then I'll know the intended deformation field and extension that I need to go through in order to produce that level of stabilizing strain in the component. And that's something that the person just has to find a connection to themselves, because it really is the underlying strain state within the component that produces the stabilization. Not as trivial to do in a complex multi-axial problem like a spring, but it can be done.
Okay, I think this question is for Karen. How do I access this technology?
Okay, this technology has been patented by NASA Glenn, and it is available for licensing. If you go to our website, you can find an informational sheet, this technology that you can download, and it's got all of our contact information there, and we'd be happy to help anybody who's interested in this technology.
Great. We've got about 5 more minutes for questions. They're still coming in. So let's get through as many as we can. Have you validated the stabilization on precipitated alloys, that is, alloys that are typically aged at 300 to 500 degrees centigrade?
Not with this mechanical methodology, but we are doing a lot of work in those systems with some of our ternary alloys, and we eventually will be applying this to it to see, if there are any things that need to be changed in this construct in order to allow us to stabilize those beyond what their inherent stabilization through the precipitation is.
Okay. The next one is, how does the SMA actuator react in a high-strain environment, such as rotor blades and hubs?
Well, again, that depends on 2 major factors. One is the amount of strain that the alloy can do, So, it depends on, what the limit surface for the alloy is. Is the transformation capable of producing 2% strain, or is the transformation capable of producing 8% strain? And that's dependent on the alloy and the construct of the alloy. It also depends on the alloy again, because certain alloys, like some of the heavily precipitated nickel-rich systems, are able to carry much larger stresses in order to generate those transformation strains. So the answer really is dependent on what alloy have you picked for those particular applications. There are alloys that we do for bearing class materials that can generate or can handle, now this is super elastically, but they can handle on the order of about 3.5 gigapascals and about 4% reversible deformation in their austenitic state. We have actuation systems that we know of with some of the ternary alloys that we're doing and developing here within our group that can handle on the order of about 500 to 600 MPa and about between 2 and 4% reversible transformation strain in actuation. So that's all I can tell you in terms of that. And if the rotor blade application falls within those limits, then it would suffice. These materials would suffice for those applications.
Okay, it looks like we've got time for just 2 more questions. Have you directly applied current to the material to induce the heat to shrink the material? And how effective and efficiently does this work?
So yes, I mean, that's a lot of people, love to do that. Unfortunately, that's typically only done with wire-based systems because of the inherent issues with how big the power supply would need to be in order to joule heat the material if you had a much larger section. So in general, with larger components, we typically do not use joule heating because it's very inefficient. And it also requires us to carry a big, heavy power supply, which is what we're trying to get away from, which is excess weight. So typically, as we go to larger and larger constructs, we do some other type of heating methodology in order to produce transformation.
Okay, and the last question for today is, can you predict the life at lower stress levels?
So we have actually invested quite heavily in doing various modeling activities in order to start to develop ways of predicting these kinds of behaviors. Unfortunately, damage is one of the hardest things to do, and it requires a lot more data than has been generated, to date within really the whole community. So, deformation and damage, in order to predict life of especially low component systems, or low stressed components, I should say, is not something that people have looked at. Now, we are currently, in fact, one of my colleagues, Osman Benefend, has been heavily developing our durability capabilities here at NASA Glenn, and we are headlong into studying the durability aspects of the entire suite of alloys that we generate here at NASA Glenn, as well as commercial alloys, to see what conditions best satisfy both actuation potential as well as durability and life extension for commercial applications. So unfortunately, there isn't enough data to date to really look at that and to be able to, even from a calibration curve type of perspective, to predict lifing of these components. What we can say is that clearly the lower amount of deformation that we require out of the system relative to what its maximum capacity for transformation is, the longer life the system will have. And in the automotive sector, they know this greatly in the sense that they're using alloys that might do in a polycrystalline aggregate 4 to 5% maximum transformation. they're designing the systems to run at only about 1 to 2% or 1 to 1.5% transformation, and they're getting millions and millions of cycles out of these systems. So the construct is pretty simple, is don't push it to the maximum that it needs to use, and you can get almost infinite life out of the system.
Okay, that's about all we have time for. So that's going to conclude today's webcast. Again, if we didn't get a chance to answer your questions, our sponsor will do their best to address them after today's presentation. Our thanks to Dr. Santo Padula, Karen Bartos, and everyone online for joining us today. If you missed any portion of the presentation, or if you have other friends who would like to watch it, this webcast will be available on demand at www.techbriefs.com for the next 12 months. Have a great day.